All right, let's dive in. We're facing a monumental challenge, securing global food supplies while water scarcity just keeps getting worse. I mean, look at the numbers. By 2050, global food production needs to jump 70%. 70. And for the basics, rice, wheat, maize, we need nearly double the output, like 140% more each year. That's what we need. But then you look at the water supply. Well, that's the headache. Projections show an 11% increase in water needed just for irrigation, yet reliable fresh water, it's shrinking. Climate change, bad management. It feels like we're heading straight for a wall.
It really is the ultimate resource crunch, and that's why today we're looking closely at a really interesting study. It doesn't just map the problem, it actually models a solution. The full title, just so you have it, is Assessing the Potential for Renewable Energy-Powered Desalination for the Global Irrigation Sector.
And our mission here is to kind of unpack their two-part strategy. First, push hard on irrigation efficiency to slash demand. And second, use cheap, clean, renewable energy RE to power desalination for the water we still need. Okay, desalination. You know, cleaning seawater or brackish water, it sounds like a perfect fix, doesn't it? Climate-independent water. But the study notes only about, 1.8% of desalinated water goes to crops now. Why so little? Why hasn't agriculture really tapped into this?
Yeah, it boils down to economics, really. Historically, it's just been way too expensive to make desal water for crops compared to traditional sources.
Yeah.
Groundwater or river water, often heavily subsidized or just cheaper to access. Desalination takes a lot of energy.
Right. But this study is basically saying, hold on, things are changing. Costs for renewables are plummeting, desalination tech is getting better. This could actually flip the script and make it affordable, even for staple crops.
Precisely. They think we're at an inflection point. They're charting a course where it's economically viable. But, and this is a big but, only if we first tackle that massive issue of water waste we have right now.
Okay, let's unpack that then. Step one, efficiency. Before we even think about making new water, just how bad is the waste in farming today?
Oh, it's immense. Irrigated agriculture uses 70%, 70, of all global water withdrawals. That's huge. And get this, the study estimates the current global average beneficial irrigation efficiency is only about 33%.
Well, 33%, so two-thirds of the water pulled out for farming is essentially lost before it even helps the crop.
Yeah, pretty much. Lost to evaporation, runoff.
Yeah.
Just not getting to the plant roots effectively. It's a staggering level of inefficiency.
And we seem stuck with old methods. Why is that? What systems are dominant?
Well, it's largely about existing infrastructure and, frankly, the upfront cost of changing. This study highlights that 86% of irrigated land globally still uses low-efficiency surface irrigation. Think flood irrigation, basic furrows in the ground. These methods might hit maybe 60% efficiency on a good day, but often they're down around 30%.
So we know drip irrigation can get efficiencies up into the high 80s, even 90s. Why is switching so slow? Is it just the money for the farmer?
It's complicated. That initial capital cost is definitely a huge hurdle, especially for smaller farms worldwide. Plus, you need training, maintenance, reliable power for pumps. It's a whole system change. So inertia keeps us wasting water because the old way seems cheaper up front.
Until the water runs out or gets too expensive.
Exactly, which is where this study's modeling comes in. They looked at a scenario they call highest possible irrigation efficiency, HPIE.
Highest possible. That sounds pretty optimistic, like a lab ideal. What does that involve?
It is definitely ambitious. The HPIE scenario projects that by 2050, all existing irrigated areas could technically hit 90% efficiency. That's basically reflecting the potential of the best available drip and microsprinkler tech.
90% globally. Wow, that feels like a stretch from 33%. Is that the only path forward in their model? Well, they model the maximum to show what's technically possible. But here's the really interesting part. The impact of just getting partway there. If we could lift global average efficiency to just 60% by 2030, still a big jump, but less than 90%, that alone cuts the estimated need for new desalinated water by 64%.
64%,
Yeah.
just by being smarter with the water we already use.
Oh,
That's
bizarre.
huge. We're basically solving almost two-thirds of the supply gap right there.
Exactly. And if you push further, aiming towards that 90% target by 2050, the modeling shows an 80% reduction in the total global desalination demand. So the big takeaway here is powerful. Getting serious about efficiency can, as the study says, alleviate water stress and can eliminate need for additional water supply in many places. It makes the remaining problem much, much smaller.
Okay, so efficiency first. That shrinks the problem by potentially 80%. But there's still that remaining 20% gap, especially in really water-stressed areas where local sources are just gone. Which brings us to part two. Renewable power desalination. How did the study model that? Right, so for that remaining demand, they focused heavily on seawater reverse osmosis, SWRO. It already accounts for about 30% of desalination globally,
And why SWRO?
primarily because its costs are falling the fastest. Better membranes, more energy-efficient systems overall. And crucially, to power these plants, they modeled using the cheapest mix of renewables available, usually solar PV, both fixed and tracking systems, and wind power. And critically, because sun and wind aren't constant, they paired these with storage. Batteries mostly, sometimes power to gas technology too. This ensures the SWRO plants run 24/7, which is vital for making them economical. You can't have that expensive gear sitting idle.
Makes sense. Okay, so the bottom line for whether this works financially is the levelized cost of water, the LCOW. This includes getting the water to the farm, right? Not just cleaning it.
Exactly. LCAW is the all-in cost per cubic meter delivered. And the study's projections show a really promising trend. For 2030, the typical global LCOW range, including transport, is estimated between about zero point 0.7 euro and a computers per cubic meter.
Still a wide range, and that top end sounds pretty steep for farming.
It is now, yeah. But look at the 2050 projection. That range drops significantly, down to between 0.45 and 1.7 per cubic meter. That reflects falling costs for both the SWRO tech and the renewable energy systems powering them. The whole setup gets cheaper.
Okay, so 0.45, 45 cents per cubic meter on the low end by 2050. How does that stack up against what farmers might actually pay?
Well, the study cites other research suggesting farmers, like in Australia for instance, might be willing to pay up to around 0.63 per cubic meter today. So what this suggests is by 2050, especially in coastal areas, our powered SWRO becomes genuinely cost competitive. And think about it. As conventional water gets scarcer, maybe subsidies disappear, pumping costs for groundwater go up, desalinated water could actually become the cheaper, more reliable option.
It really could shift the whole economic picture. But water problems are always local. Where's that remaining desalination demand concentrated, even after those big efficiency gains?
Extremely concentrated, actually. Three countries, China, Iran, and Pakistan together account for something like 50–55% of the total projected desalination demand in both 2030 and 2050.
Wow. So success in those three is absolutely critical for global food security using this strategy.
Definitely.
And where do the costs get really tough? Which regions face the highest LCOW?
That would be Central Asia. The study found countries there face average costs ranging from 3 up to almost 6 per cubic meter. Really high.
Whoa, 5.80. That's like 3 times the global high-end projection for 2050. Why so expensive there?
It comes back directly to that transport and pumping cost inside the LCOW calculation. Central Asia is landlocked, so any desalinated water, likely from the ocean or maybe a large inland sea, has to be pumped incredibly long distances, potentially across borders, maybe uphill.
Ah, the sheer logistics. Pumping water hundreds or thousands of kilometers inland, that's the killer cost, not the desalination itself.
Precisely. It just underscores how absolutely vital maximizing irrigation efficiency is for those inland regions. It's their main lever.
Makes sense. And the study also noted that even in places where desal might become cost-effective, like coastal China or parts of the U.S., water stress still remains high.
Yeah, that's a key point. Even if agriculture gets super efficient and has a new water source, you've still got huge growing demands from cities and industries in those same areas.
Right, everyone's competing for the same limited regional water, even if farming's footprint shrinks. It doesn't solve the whole regional puzzle.
Exactly. And there are other costs, sort of hidden ones, that aren't fully captured in those main LCOW numbers we talked about. The study flags the environmental issue. What do you do with all the leftover concentrated brine? Discharging tons of super salty water back into the sea isn't simple.
Right, dealing with the brine. That adds cost and complexity, doesn't it?
It can, significantly. In sensitive marine environments, proper handling and discharge systems could add up to 30% to the final water cost. And another really important point. The LCOW figures cover producing and delivering the water to the farm. They do not include the massive investment individual farmers would need to make to upgrade their own irrigation systems, ripping out old flood channels and putting in the pipes and drippers needed for that high efficiency.
Ah, that's a crucial piece missing from the farm level economics. A huge upfront cost for the end user. Okay, so let's try to wrap this up. We've covered a lot of ground based on this one study. Our deep dive into assessing the potential for renewable energy-powered desalination for the global irrigation sector really lays out a possible path forward. It shows that aggressively boosting irrigation efficiency, really pushing towards that 90% mark, combined with increasingly affordable, renewable-powered SWRO desalination. Well, it offers a viable way to secure water for key crops by 2050, especially in those high-demand coastal regions like China, Pakistan, Iran.
It does paint a plausible technical and economic picture for optimizing traditional agriculture. But, for a final thought, it's worth looking even broader. This study focused on rice, wheat, maize, but other researchers are working on ideas that kind of bypass traditional fields altogether. Think about producing single-cell protein, something like Solein is an example using just CO2 from the air, renewable electricity, and a tiny bit of water. We're talking maybe 10 liters of water per kilogram of protein. It's a completely different way of making food. So it leaves us with a big question, maybe for you listening. As water scarcity bites harder everywhere, pushing up costs, where should the focus be? Doubling down on optimizing traditional farming, like this study explores? Or should we be accelerating these radically different, potentially resource-independent ways of producing food for the future?
That is definitely something to chew on. A fascinating look at potential futures for food and water. Thanks for walking us through it, and thank you for joining us for this deep dive.